So before we get to the book online, which is going to, you should have a hard copy already. I want to introduce this concept of motion in one dimension. Basically, chapter 2 is going to start off that way. And so that's what we want to do here before we get into the text. So motion in one dimension, we're going to call that motion, well, it's commonly called kinematics. It's like dynamic motion, or kine meaning motion, matics, mechanics, or dynamic motion. So specifically, that's motion with no regards to its causes. We're just looking at things moving at a constant speed or with a constant acceleration or changing speed, changing position in a certain amount of time, and we don't care what's causing the motion for right now. Soon we will be concerned with that when we get into concept of forces, and then we're going to see how forces relates to energy. And then from there, we'll start looking at momentum and so on and so forth. But right now, we're just looking at motion with no regards to its causes, what causes it. So the first perspective of this motion will be along a straight line, and that straight line will be the x-axis. Cars rolling along, you walking, balls rolling down, horizontal line. No projectiles like baseballs and footballs in the air, which follow the path of an arc. So in that situation, we'd have to look at both the horizontal x-axis and the vertical y-axis simultaneously in order to describe what's going on with that. Right now, we're choosing the very easy case, one axis. Even easier, the easiest axis, the x-axis, because now we don't have to deal with gravity, which is not too bad. It's just another type of acceleration. So the motion along the x-axis will be acceleration caused by you pushing or pulling something, put your foot on the gas, put your foot on the brakes, that sort of thing. We're going to treat all objects as particles. So that helps in a larger sense, especially when we get into forces, when we have to identify all the forces acting on a particular object. So instead of modeling or drawing the object itself, like, drawing a little sketch of a car with wheels and all that stuff, we just treat it as a dot, treat it as a particle. So that just helps, with the analysis. Now, this is not necessarily 2.1 in your book online, but the first section or the first idea of this motion in one axis will involve the concepts of position, velocity and speed, and time. We're going to see in the CVPM that there's going to be 4 slots of things that we can measure. If we were in the classroom, we would be seeing this little car that I have that moves at a constant speed. And then one of the things that I ask students is like, out of what you see there, what can you measure? Ideas, we can measure, the length of the car, or how fast it's going, the position, how much time it takes, all these things. And so we're going to be filling in those 4 boxes on the CVPM that relate to these things here. These are the things that we can measure. So even if you wanted to start filling in the blanks there, we can measure of this car or of this object. We can measure its position. We can measure its velocity, measure its speed. We can measure its time. And we can even measure its weight or mass, or, number of things we can measure. So it's like a brainstorming thing. So again, the definition of position is that that's a location of a particle relative to a chosen origin. Now, in math classes, our origin is the 0, the middle of the graph. But in physics, we can choose any place to be our origin. It's an orientation or a frame of reference. I don't want to start at 0. I want to start at 2. And then I want to now travel to 5. What is my displacement in that situation, which we'll talk about in a second? That would be 3. Okay, now next time I want to start at 0, and then I want to travel to 5. What would be my what would be my displacement in that case? It would be 5 as opposed to 3 in the previous case, because I start at a different point. So I can start anywhere to get any displacement, which is coming up. But position is just a finite point, just any location of a particle relative to a chosen origin. So now let's consider a particle's position on a number line. You've seen number lines in your algebra classes everywhere. So now we're going to translate what we see mathematically into actual physics. So the x-axis represents 2 directions. On the number line, the positive part of the number line is the easterly direction, noted as E. And then the left-hand side of the number line is west, noted as W. So when you're traveling towards the east, you are going in a positive direction. When you're traveling towards the west, you're going in a westerly direction or negative direction. So as we see here, this position of this car on the positive x-axis, its location in space or its position is plus 30. What that means is that I am at a position of 30 meters to the east. The plus and minus signs are not going to be representative of integers, as we know in math. In math, it's an integer, but in physics, we're going to take that integer and translate it to something real. So plus 30 in physics means I'm 30 meters to the east. Negative 10 meters means I'm 10 meters to the west. That's pretty much all there is there. And so I also have north and I have south. In the positive y-axis, that represents north and of course positive direction. And the south, it's a negative direction. So we will be considering this axis when we get into gravity, when we get into free falling objects, objects falling under the acceleration due to gravity, which is a constant value. So what is this xi and xf? Well, glad you asked that. Xi means the initial position. Say, for example, I want to start at 30 meters to the east. So I'm trying to see if I can fit that in somehow here. Any questions so far? Hopefully that is relatively okay. And then we can translate that to your textbooks, because I think in chapter 2, it definitely discusses this, but then they introduce vectors, which I don't like how they did that simultaneously, but we'll circumvent all that. Okay, so plus 30 meters is not an integer. That means my position is 30 meters east, or to the east, huh? And with respect to our definitions already, that will be 30 meters from our starting point. Let's say our starting point is the origin in this case. But if my starting point was 2, now my starting position relative to that would be 28. So it's all about where you start with regards to your chosen origin. All right, and so therefore, likewise, 10 meters here, negative 10 meters would be 10 meters west. So in effect, what you're looking at here is a vector. I'll be introducing that even more so down the line. But all a vector really is a quantity that has a number in it and it has a sign. The number, the initial position would be 30. The sign would be the plus sign. That represents where you're going or where you are. I'm 30 meters to the east. So essentially, this is a vector. Sorry to squeeze that in there. A vector has a number and a sign. In technical speak, you will see magnitude and direction. Magnitude means number, direction means sign. Try to simplify these terms best as possible. So the xi is the initial position. The x final, xf, is the final position. There is something in physics we call displacement. Displacement is a change of position. It's like distance, except that displacement has a number and a sign. Distance just has a number. It's football season. Those of us who, like football and all that stuff, I try to do my initial problems relative to the sports seasons. But in football, for example, if you have like a kickoff and the guy catches it at the goal line, if for some reason he, runs all the way down to the opposite end zone and then runs all the way back, he has traveled a distance of 200 yards. But his displacement will be 0. Because as we're about to see, displacement is the change of position, which is the difference between final position and initial position. The initial and final positions are the same. Therefore, 0 minus 0 is 0. But he traveled 200 yards of distance. So in physics, we're only concerned about what happens between the final and initial. We don't care what happens in between. It's immaterial. If I drive to Berkeley straight up from LA County, I have traveled a displacement of about 400 miles, to convert that to meters. But if I went on the PCH and did all the meandering around and the switchbacks and I still traveled a displacement of 400. It's that my distance is crazy. And so that's why, it's not feasible to take the PCH if you want to do, travel very fast. It's going to take more gas, it's take more wear and tear on your car. So it's better to look at displacement over distance. So displacement is a change of position. Here is the definition. Here is the equation for displacement. Delta x is going to represent our displacement. Delta x is final position minus initial position. As we saw above, my final position is minus 10. That's my actual whole position. That's my location at the end. Subtract my location, my position at the beginning, which is plus 30. So negative 10 minus 30 is minus 40. That means that I have traveled 40 meters to the west. And if you see the paper on your number line, I won't scroll up for people writing. You will see that you have traveled west, and we got the actual value. In physics, we're concerned with how much a lot of times. I've gone 40 meters towards the east. First, I went 30 to the origin, and then I took another 10. Should make sense. And our subtraction, everything checks out. Negative 40 meters or 40 meters west. Pause while you guys write that. Now, like I said, the distance would be just 40 meters, right? But if I went from 30 to 10 all the way back to 30, my displacement would be 0, but my distance would be 70. You guys see that? Because I will have traveled 40 way over there to minus 10, and I go back 10, and then, okay, it'd be 80. My bad. Yeah. So you just add it twice for distance. but for displacement, that'd be 0. So physics, we're only concerned with displacement. What happens between the final and initial positions? That will become clearer as we do more practice problems and see more concepts of physics, because we're starting with our definition of displacement, the final minus initial position. We're going to see that in future physics, when we're talking about the difference in momentum, change in momentum, final momentum minus initial momentum. It's the same concept that permeates all of physics, really, at least until we get to the realm of modern physics, quantum mechanics, particle physics, nuclear physics. The concept of displacement is pretty much either takes another idea or null and void. Null and void with respect to classical physics. Okay, now we've talked about displacement and distance. Let's talk about velocity. Right, again, very important when we go to our CVPM. Now, velocity, which is constant velocity particle model. Let's say the particle moves a certain distance in a certain time interval. Then we can calculate a velocity. That's all it is. Velocity is a change of position divided by a change in time. V equals delta x over delta t. There's the definition of velocity in words. Velocity, change of position, change in time. And here's the equation. V with an arrow, because velocity, like displacement, is a vector. It too has a number and a direction. If you're traveling towards the east, you have an easterly velocity, or velocity, they have a number and a direction towards the east. And likewise for the west. Also mathematically, when you have a vector divided by a scalar is just a number, time is just a number, you get a new vector. You multiply two vectors, you're going to get a scalar. When you multiply a vector and a scalar, you're going to need a new vector. When you do a cross product of two vectors, you get a new vector, blah, 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 blah. Well, that's just me ranting. We won't have to do too much with, say, cross products in this brand of physics. But anyway, delta x, final position minus initial position, which we've defined above. Likewise, delta t, t final minus t initial. Delta anything is final minus initial. Change in magnetic field, that creates current. Delta B, magnetic field represented by B, BF minus BI. So let's get an example. I was doing this from the AP perspective, but still an example that can relate to us. Let's say that we have a car at 30 meters east, plus 30, and final position, negative 53. And it takes 50 seconds for the car to change its position from 30 to minus 53. What's the velocity? Well, by definition, V equals x final minus x initial divided by TF minus TI. Negative 53 minus 30 over 50, negative 83 over 50, negative 1.7 meters per second. That means that my car travels towards the west at 1.7 meters per second. That's the rate of change of position. That's how much position I've changed every second. Every second, I've changed 1.7 going west, 1.7, 1.7, 1.7. Chime in anytime you have any questions or comments. But hopefully that's all right. Negative 1.7 meters per second, or car is traveling 1.7 meters per second to the west. So mention there. All right, here's the fun stuff. Velocity, delta x over delta t. This is exactly the physical analog of your slope equation that you've seen forever. It's all a slope. That's all it is. When you have a graph of position versus time, and you take the slope of that graph, you get a velocity. Because look at it. Look at the form of the equation. M for slope, changing y over x, rise over run, right? Well, what's the rise in the physics case? Your displacement over time. So your displacement will be in the y-axis and your time will be in the x-axis. That's why you have this x here and t there. This would be called a position time graph. We're going to see that. It's a CVPM, a position versus time graph, or a position time graph, or an x-t graph. All those mean the same thing, position versus time. And the graph, you graph things, you plot points, blah, blah, blah. When you take the slope, you get a velocity. You then can say from the graph, you can interpret data from the graph and say, my car is moving at a particular velocity because I took the slope of that position time graph. So let's look at this axis here. You say y-axis, well, x is the x-axis, well, x represents position. In time, we'll be able to make that switch. But this is position, not displacement, position. We, for the sake of simplicity, we don't graph displacement versus time graphs. We graph position versus time graphs because now we can label all the points as locations. For displacement, it'd be a little odd. We have to take all the positions, subtract, and put the result there. It's just too cumbersome for that. So position versus time. And I think I had some other data, but I just graphed some, arbitrary data. I just made up numbers. Say this is 10, I graph my line here, and then it took me 2 seconds to change that position. What's the speed? Well, the speed or the velocity is just the slope. Final position, 10, initial, 0, over 2, 2 minus 0. Final position, initial position, final time, initial time. And I get plus 5 meters per second. That means that my car is traveling towards the east 5 meters every second, 5 meters per second. And just to show you again that the units of velocity of meters per second, this is in meters, this is in seconds. Meters divided by seconds. Okay. So that is another way to look at velocity, look at it graphically, interpret data, do it mathematically. And we'll see now how to even get to this graph. Question. Yes, I can, no problem. Velocity definition was the question. Here we are. I guess right here. Hopefully that's it. So again, velocity, change of position over change in time. We're going to see in a moment, acceleration is change of velocity over change in time. That's down the road when we get into constant acceleration. And then from constant acceleration, we're going to be creating our motion equations just from looking at a graph. So we're going to see the power of the scientific method in robust fashion. We can get everything we need from graphs. That's why graphs is just so important in physics. You cannot really get away from proving something without interpolating or interpreting graphs. Like, put graphs up, it's visual. Those in the know, you have experience, you can look at a graph and just see what's going on with it. Does it represent linear data? Does it represent nonlinear data? Meaning, is it a line, and like in this case, or curve in other cases for nonlinear? Okay, so let's go now to our next slide. the importance. So again, more sample displacements. I just want to drive the point home here. Again, our number line, we're on the x-axis. Pretend you're in a car. You start at you start at negative 15 meters to the west. You want to go east. Going to grandma's house, right? What's your displacement? Who cares about the distance? You can calculate the distance. It'd be 20. All you're doing is adding the numbers with distance. You're at 15, another 5, 20 meters of distance. Now, in this case, the displacement is the same as distance, but not always. As we said it, as we illustrated in the football case. Okay? It's not always the same. They're not always equal. Anyway, for this sample displacement, delta x equals x final minus x initial. Final position is 5 plus 5 because I'm 5 meters to the east of my origin or in the easterly direction. So all things over here is plus. Minus 15 because I start at negative 15. So I don't do 5 minus 15. I do the actual position because the position is that number and its sign. Unless you get the wrong number, you will get a negative answer, but you traveled east. That will be inconsistent. It should show you visually that your subtraction was wrong. You have to subtract minus it. So 5 meters plus 15 means 20 meters east. I have traveled 20 meters to the east, 15 here and another 5 east. Went to the right. And likewise, if I go the other way, initial position of 15, and then I stop at negative 7.5, negative 7.5 minus 15, that gives me minus 22.5. Again, I went to the west, I went left. So my position change was 22.5 meters west. I can write it in the math form, or say 22.5 meters west. And like I mentioned earlier, vectors is just, they are just quantities that have magnitude, that means a number, and a direction, sign. So our vectors so far are displacement and velocity. The other vectors that we're going to see, acceleration, then we're going to see force, then we're going to see momentum, then we're going to see, let's come after that normally. The universal force of gravity, torque a little bit, maybe we'll dive into that a tiny bit, but those are all examples of vectors. They have a number and a direction. So in physics period, we're permeated with vectors. It's all over the place. Now, okay, velocities, okay. Now the velocity that we're going to see in the CVPM, which is constant velocity particle model, is going to be an average velocity. We're typically going to be dealing with nothing but average velocity. And those are just velocities that deal with final position minus initial position over final time minus initial time. We're seeing on average what your velocity is for an entire trip. But in reality, your average velocity is not ever, or mostly not ever, the same as your average. For example, you're traveling somewhere. You calculate your average velocity when you know your final is this and final is that. But along the way, you could have traveled, then you get like say 85 miles per hour. I'm gonna go to miles per hour. But let's say at some point along the trip, you went 100 miles an hour. Some other time you may have gone 55 or 62, but on average, you went 85. So the average is not the same as, say, moments of velocity called instantaneous velocity. We won't deal with that here, but your average velocity is the most important. And I was telling the other class about derivatives. This dx dt is the same as this delta x delta t. Same. Exact same concept. It's just written this way for calculus purposes, because calculus, we treat it differently, and especially when we get to integrals and nice fun stuff. But we'll be concentrated here, the algebraic version of average velocity. So again, I'll pause. Questions? Hopefully that is all right. If I'm going too fast, let me know. Okay, so one, velocity is the slope or derivative of position versus time. Don't worry about derivative. That's the same thing, same thing. Math people get a little cringy at me. I know that, because definition of derivative is not as simply put as slope is a whole functions minus another function of x minus function of position. It's not as simply put in terms of derivatives go, but overall it's basically the same. Second thing, delta x values will be on the vertical axis and delta t values will be on the horizontal axis. And that's going to be important. I'm going to show some data here in a second. So when we see our CVPM, and like, for example, if we were in the lab, if we were at school, you would be collecting all of these positions and all of these times. One person in your group would record the position, and somebody, like normally what I'd have for the CVPM, I have like one person in your group say 1, and then they actually put a popsicle stick down to measure that position. Somebody says 2, and the same person says 2, and another popsicle stick, and 3, and popsicle stick. So like you can kind of, it's not going to be exact, but you can kind of get a picture of, hey, this car is actually moving at a constant rate. It's 2 meters every second. Wow, that's goes first second, 2 meters, second, 4, 4.1, something like that, a little bit off, but generally it's roughly the same interval. And so that's going to be important for our data collection. All right, can I move on to the next slide? Everybody still writing? Okay. So now, like I said, let's take a look at some simple sample data. I don't know how they do it in your math class. I think X versus Y, domain and range, it doesn't really matter. But in physics, the way I like to do it is I like to have my range on my left. I like to have my Y-axis first and then my X-axis data. So we were talking about last time, like dependent variable, independent variable. Go over that. Yeah, I mean, make sure that you have a basic idea of what those two things are, but we won't have to worry about them explicitly when we're graphing data. Just put everything in the y-axis on the left-hand column, x-axis on the right-hand column. And typically, once we're getting introduced to data via the CVPM, all of your time data, your 1 second, 2 second, all of your time data will be in the right column, because time is always going to be that independent variable. Yes, you can measure it, but I would say there's a number of ways to clarify that, but the one quantity that you are directly want or observe is your positions. Because time is going to be there for any type of data. So we just normally put time in the x-axis. It is the quote, if you will, universal independent variable. And that's always going to be in the x-axis. So our range of values will be the y versus x. And we just saw that this is math, but we just saw that your position data would be in the y-axis and your time data x-axis. So these are all axes. Domain and range, right? Oops. Okay. Now we take that math stuff, the axes, and we translate it to physical data. So as we saw earlier, that the position is in the y-axis and it's measured in meters. Time is in the x-axis. And I just put some arbitrary data in here. So let's say at time 0, we're at position 0. Everything's good. Now in the first second, we travel 5 meters. Okay. Somebody put the popsicle stick down in class at 5. 2, somebody put the popsicles down at 10. 3, somebody put it down at 15. 4, somebody put it down at 20. We collect the data. Somebody, and the third person in your group is recording this stuff. Okay, 5, 1, put in the columns. And then you all look at it and you see something nice happening with the data. You see that every second, it goes the same amount of meters. 5 meters every second. 5 to 10, 10 to 15, 15 to 20. This would be an example of linear data. So as I say here, linear data is data that has increments that are the same for every point in time. You have the same increment, the same gap for every moment in time. 5, 5, 5. That automatically tells you, without even looking at a graph, without even doing anything, you are going to graph a line. This is linear data. Now, for example, if it goes from 5 in the first second, and then it goes 17 in the second, and then it goes 35 in the third, now you have nonlinear, because the increase is so dramatic. And even decrease, because as we will see when we get to acceleration, that for a car that's speeding up, the gaps are dramatically large. And then for deceleration, they get dramatically smaller until you come to a stop. So these go 5, 17, 35, 62. And then when you start to slow down, it goes, all right, maybe 67, let's see, 70, then it goes 67, 65. It just gets dramatically smaller and smaller after getting dramatically larger and larger. So linear data have the increments are the same for every point in time. Everybody see that? Hopefully everybody's tracking that. And now we take this data. So this would be part of the experimental process where we're interpreting data. We're doing our experiment and we're going to interpret what's going on. We're going to explain what's happening. So like I said, the X data will be in the Y-axis, 5, 10, 15, 20. And then the time data will be in the X-axis, 1, 2, 3, 4. So we plot the points, 5 and 1, 10 meters in 2 seconds, and so forth, 15, 3, 24. And typically in real experiments where there's error and that comes in, how you measure it, how you look at it, are you looking at it in terms of millimeters, decimeters, or whatever, the data points are going to be kind of off the best fit line. But in this case, it's pretty much on there. It was a pretty sound experiment, so you're okay. A little bit of gap there, but this best fit line, what that represents is the average in your data, AKA the average velocity. Get it? This line of best fit is representative of your average velocity. The data points, if they're all on the average, tells you, or will, as you see more examples, it tells you that your experiment was pretty sound. There was no error in it. The data points are off. That doesn't matter. It's cool. But that gives you an indication that there was some little error there. That's okay. As long as the error wasn't, very, very large. And we'll be dealing with percent error in time. I think I gave an example last time, but in time we will deal with that. So the line of best fit will still go through all those data points. You don't connect any dots. That's now distance, and that's just incorrect. So you always draw a best fit line through the data points. And these data points that come off axis represent some kind of error in the experiment. If the error typically, 10% or less, you got a pretty good experiment, even if those data points are off. So in math, we would take the slope, and that would be equal to 5, just the number. But in physics, that represents 5 meters per second, plus 5 meters per second. This is a positive slope, whereas the line that going down here like that would be a negative slope. We're still in the positive domain, but the velocity will be negative. We're going towards the west. Even though we're still in east, we're going to the west. That's what that would represent. This plus 5 meters per second is 5 meters per second towards the east, or in the easterly direction. Now, we may have seen this. We graphed this and took the slope. The graphical representation of this slope would be a straight line. Why is that? Because this velocity is constant, like the slope is constant. Once we take that slope, there's no other slope you can get. You typically take the slope between the most extreme points, but generally speaking, that slope will exist between any 2 points in that. Won't be entirely exact all the time, but typically speaking, you're going to get the same slope everywhere. For example, we did the most extreme, 20 minus 0 divided by 4 minus 0, we get 5. So if we did 15 minus 5, we get 10. 3 minus 1 divided by 2 is also 5. So the slope is constant slope between any 2 points, and those 2 points, that slope won't change, as you can see. And that slope represents a velocity anywhere, everywhere. It's your average. So your best fit line represents your average velocity. Any questions there? So best fit line in your math is your average velocity. Best fit is average velocity. Always average anything, average acceleration, average force, average momentum, average magnetic field, average electric field. This best fit line is your average. And so this line is going to be horizontal to represent the constancy of that slope. This careens along in a straight line, doesn't change. Your car is in cruise control. Every second I'm going 5 meters per second, just chilling. 5 meters per second, 5 meters per second, 5 meters per second. You put your foot on the gas, this thing is going to slope up. It's going to look like this. But that's later. Okay, everybody have that? Go to the next slide. Okay, so like I said, okay, well, this is brief. I'm not going to go beyond this slide because it gets crazy. So now we have the position in the y-axis, time in the x-axis, 0, 0. Let's say everything's good in the first second. Okay, it's all good. First second, go 5 meters, but then in the second, I go 12. Third second, I go 25. Fourth second, go 43. Fifth second, go 65. So there's a dramatic increase. This is no longer linear. The gaps are not even the same. 7, 13, 18, 22. So way out of whack. This is nonlinear data. We won't be dealing with this today, but I want to give you the difference between linear and nonlinear data, where the increments are not the same every second. Not only not the same, dramatically different in some cases. This will be representative of an object accelerating or speeding up. Its position is changing dramatically every second. You put your foot on the gas, you're 0 to 60 in 5 seconds or whatever, because you dramatically increased your position, change your position. But that's just a little bit on the concepts of, again, I'm gonna go back. Kinematics, motion in one dimension. We're gonna go along the x-axis. Motion with no regards to its causes. Moving along the x-axis for now, and serves as an intro to our CVPM. Does everybody have a CVPM? Who does not? You can send me a chat private if you don't have it. I'd like to know who doesn't have it. If everybody has it, I want to get a chat so we can move forward. So today is more content intensive, but you know, the next time we'll break out and do some stuff. Okay, if everybody has their CVPM, let's go right there to it. New share. All right, I've written on it before, so it's going to be easy to follow on. Everybody have this? Constant velocity model, either in your hand or on screen. I like this because I can save this as a Word document from PDF. So now I'm able to write on it pretty good. Okay. Come on back up here. So we have just introduced this concept of constant velocity. Constant velocity means the slope of your position time graph is constant. Therefore, the velocity is constant. I think I want to go back here just a moment and say something about that. So one thing to keep in mind is that when you are looking at a position time graph, the slope of that graph, the slope of a position time graph is the average velocity. That's really what we do in physics. We take math, we translate it. That's not everything, but that is a large bulk of it. So you get to PhD level, you've got these crazy inverse tangent graphs going along, cotangent this, and you're seeing intersections of an arc of a circle with a cotangent graph, and they intersect at a certain point, and you know, the point of intersection is the eigenvalue. Okay, and I know what those intervals stand for. That means that the function goes to infinity. So you're always interpreting math. in physics. You know what you're looking at. You don't use all of math in physics, but you use what's necessary. You have your toolkit with you. You can use all of the math, every concept that you learn in math, but you don't need it. You don't need it all. So that's what we're doing here. The slope of a position time graph is the average velocity. And likewise, when we get to it, the slope of a slope of a velocity time graph is the average acceleration. The slope of a force versus mass graph will be the acceleration. The force of the slope of a force versus displacement graph. Force versus displacement, let's see. Okay. The slope of a work or energy versus displacement graph will be a force. So all of these type of graphs that are divisions, velocity delta x divided by delta t, all of those represent slopes. That's all they are. They are derivatives in calculus. They always give you some new quantity that is a constant. The data you're dealing with is linear data. You can have divisions where you have nonlinear situations, but typically in our context right now, slope of a position time graph is the average velocity. Slope of a velocity time graph is the average acceleration. So I just want to get back on that, and then let's get back here. So for more context to help us. So this constant velocity particle model, again, I was going over the difference between, yeah, okay. So again, a velocity plus 5 meters per second we just saw. Speed, I think I mentioned that earlier. Speed is just a number. Like for example, you're in your car and you look at your dial in front of you behind the steering wheel, that's the speedometer. It measures speed. But that speed, as you look out the window, that whole system of you looking out the window as you're looking at your, as your speedometer is registering this number, that's a velocity. You know where you're going and you know how fast you're going. That's a velocity in real life. Probably didn't know you were doing that, but that's real time, real physics, real actual phenomena. Physics is just the study of real stuff. We're doing our best to quantify everything as much as possible and then verify it by experiment. And others verify that or say, no, that's wrong. Try again. That sort of thing. So if you have this packet up available, we're going to start filling in some blanks here as if we were in class doing the lab. So until we get to this thing called Labster, we'll kind of do these things together. And it serves as a basis for us to do problems in the online book and assignments and stuff. So like I said here, the front of each model package should serve as a storehouse for things you'll want to be able to quickly look up later. We will usually try to give you some direction on a useful way to organize the space. So this is just basically, okay, I'm brainstorming, what can I measure? The physical quantity we talked about so far is position. You should now be reminded that a position is a location in space. Something quick, description. Its symbol is X and the units are meters. I think I accidentally wrote that. So let's write this up. We have position, location in space, symbol, X, measured in meters. Some form of meter, it could be centimeters. Time. The day I was doing is like, oh, how do I define time? Amount of seconds, or you might give me something else. How would you define time? If you just throw it out there. Anybody? Because it's not always just seconds. So, what would be another better way to describe time?
Minutes.
Well, I mean, yeah, we can use it in terms of some units. We have all kinds of time units, but maybe more abstract or global definition, like the passage of moments, or I don't know, maybe that's more as transcendental or esoteric or way out there. Measurement of moments. For the sake of argument, we'll just write an amount of seconds here, because we're always going to measure it in seconds. Units T, units seconds. So we also can measure physical quantity of velocity, which is change of position over time. Its symbol is V, and its units are meters per second. Speed, some other kids in other years, oh, we can measure the weight of the car. Yeah, sure, write it in there. Weight would be, mass with respect to gravity, mass times gravity, but or how heavy something is. Well, they probably won't know the mass gravity part, but speed would be the numerical part of velocity, like I showed here. Speed is S, the number. Velocity is the number and the sign. So the numerical part of velocity, S, meters per second. So in your packet, we will not do a summary because we didn't do the experiment. It's just kind of, we'd be making up what we didn't see. Like, no, I'm not gonna have you do that. Let's go to the other part. If we were in class, you could sketch and label the experiment setup. Like, I don't know, you don't have to do this, but like, probably draw a meter stick, huh? Got plenty of those in there. We'd have a meter stick, we have the little car. Can't draw. Yeah, right? The car and somebody's timer. Right? 6. Something that it doesn't have to be perfect. This is, don't have the art teacher yell at me. Druzy, formerly known as Mrs. K, but anyway. So yeah, we can just sketch and label. She's the art teacher, right? This is her associated. Yeah, they're all first name basis. So what could we measure? How could we measure it? Well, obviously, we can measure position of the car at each moment. What else could you measure? Think about this car moving along. And I would have had a Khan Academy video, but I heard this, when I show videos, it's kind of choppy. I don't want to do that. Kind of ruins it. Anything else you can measure? With a car, you get just think of this, I have to change your imagination for a moment, but this car is moving along. Anything else you can measure? Any ideas? Don't be shy. Anybody say something? Could we measure time? everybody here? Okay, everybody's there. All right. Okay, so I think we can measure time too, right? But there we are. So we could measure. This one person say, you can see this. Can you see it? Had a question. Okay. But yeah, obviously we can measure position of the car at each moment with a meter stick, huh? Where's my thick? Okay, yeah. Yay. All right. So now the objective. Generally, how I like to help you guys generate the objective is like, all right, you've measured this stuff, you measure position, time, weight, whatever. Is there something in all those measurements? Could you describe a relationship between two or more of these quantities? Is there something that you could relate? Are there any quantities that have some kind of um, correlation, or um, they that that they work hand in hand or side by side? Uh, Something to that effect, some kind of a brainstorming session to kind of get you to see, okay, I measured all this stuff. What can I now describe? Right? Is there something you can? And one thing you can is we can describe or find the relationship between position and time, because we, even though we can actively measure weight, what we did, what you would have done is mark a position for one other student saying 1, 2, 3. So there's positions being measured, there's time. Is there a relationship between the two? Take all the data, put it into a chart. Let's see if there is. We believe there is. Our objective, our hypothesis, let's say, is to find the relationship between position and time. So again, as I mentioned earlier, with the other sample data, I started off with 0 position, 0 time. 1 second, I went 5. Second, I went 10. My gaps are the same. This is linear data. And now I'm going to take my data and graph it as I did earlier. So it's the same kind of scenario. I'm just repeating it. I want to erase this second, because that's a special type of situation. It describes average velocity, but it's different. Okay, as we saw earlier, average velocity is delta x over delta t, final minus initial position over t final minus t initial. If we were to do this in terms of math coordinates, we know the time is x-axis. That would be the first point in our, what do you call it, point, first value in our point, t final and x final, minus t initial over, or t initial, x initial down here at 0.
Excuse me.
Yes, yes.
I can see it.
You cannot see this screen. Okay, let me stop this share and then reshare it. Okay. Can you see it now?
Yeah.
Good. Like I said earlier,
Uh-oh.
great. So, like I said before, the coordinates. So we have before that, I got a question. Can I go back to the x meters? Yes, yes. This right here, yeah, it's the same chart that I had the previous um, previous slide on the smart board, but yeah, same data. Again, this is linear. Gaps are the same. Nonlinear would be something crazy. 5 to 20 to 45, you know, all that. So now we can take the slope between these points, and then we get the same slope as before, which is going to be 5 or plus 5 meters per second. That's the velocity, meaning 5 meters per second towards the east. And as I said, in physics, we interpret math like all the time. What is this math telling us physically? Or what can we say about what is physically happening from what we have, you know, graphed mathematically, or our mathematical relationship? So in math, this is a point slope equation, form of the line, or slope equation, blah, 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 whatever they call it. Y equals mx plus b, where b is a y-intercept, x is the x coordinate, m is the slope, y is the y coordinate. In physics, that represents, at least in this form, it's our position is on the y-axis equals the slope, which is velocity. The x coordinate is time. And then in our case, we have no y-intercept, so it's just 0. Or so therefore, this equation would just be x equals velocity times time, which that is the case if we were just looking at the equation without the math background. Because we know that velocity is x divided by time. Therefore, I want to solve for x. Multiply time by both sides, I get x equals vt. So it all just works itself out. Any questions? So on this graph here, where it says graph your data to see if there's a relationship, why, yes, there's a relationship. It's a linear one, as we know from earlier, that the data is linear, directly proportional. Velocity is directly proportional to position. How do we know that? We can describe it in a number of ways, the relationship, that is. Velocity is x over t. This is directly related. This is inversely related. So if my time gap was very short, my velocity would be very large. It would be constant, but it would be changing at smaller intervals. I would be going 5 meters in, say, 0.5 seconds. Or, and then second number 1, I've already traveled 10 meters. Still constant. I just had a larger slope, or a larger initial speed, and my average is going to be greater than this average here. So this second equation, x equals vt plus 5. Well, now I have a y-intercept. What do you think that tells me here? This plus 5. Any ideas? No ideas. So this screen is showing guessing. Well, the plus 5 in math, the y-intercept, in physics, that tells us that plus 5 means I didn't start at 0 this time. I started at 5, and then I just carried on like this. Let's say that I had, still a constant slope, but the slope is going to be slightly different. You can see that already. It's not the same steepness, if you will. So the slope is going to be different. It's going to be lower, and that means it's going to have a lower average velocity. So this y-intercept here tells me that I had an initial position. I started someplace other than 0. Plus b times time equals x here. And I say x2 because that's my second line. That's my second position. But the basic equation of this line is x equals vt. That's all we need to worry about. I just did this here as a another example with the y-intercept. Put the y-intercept to use. So in your packet, or the packets like it, I would have had you use pencil, label your axes with symbols and units. Let's see, symbols and units. Graph, give the graph a title. We can say position versus time. Draw a best fit line. We did that. Don't connect dots ever. Find the slope using points on the line, not the data points on the line. Why is that? Because the line of best fit represents your average velocity. That's why that is important. Write the equation of the line using the variables from your axes. Don't default to y and x. Make sure the slope and intercept have the correct units attached to the numbers. So that's what we did. X equals velocity times time. We just didn't say y equals x, blah, blah, blah. So, wow, we're coming up on the end here. Okay, 5 minutes. So one thing I wanted to give out today, and I'll leave as an exercise for we meet again tomorrow. Good, because I want to continue with this. Do we meet tomorrow? Oh boy, we meet Friday. Okay, so let's take a look at this. Maybe not. I think that's going to be too much explanation in the last 5 minutes here. But what I would like us to do for homework for Friday is everybody at practice 2 comparing position versus time graphs. That's where I want to go. Because we've seen something like it. I just drew it. I like that. Does A and B have the same slope? Just by looking at it?
No.
No.
Oh, no, they do not. Okay, A is a steeper slope and B is slightly less. So that means that which one is going faster then, A or B?
A.
Absolutely right, because the slope is steeper. That means its velocity is greater. Now, in these guys, I'm going to have you describe things. A, do the cyclists start at the same point? Do they? Well, I have the answer here. No, the cyclist, right? You can see that already. No, cyclist B starts at a point other than 0. B is ahead, right? So I will just kind of, there's other questions associated with that. So I want you to do, let me see if I can run this page, that one, and I want you to do page 6 and 7 for Friday. Alrighty? I'll put that up in Google. Any questions?